continuity of a function in two variables. Before this, let's remember the continuity of a function in one variable. Let's suppose that y equals jx is a function defined on an interval ab, and let's suppose that the point x0 in this interval. So we will say that the function j is continuous at the point x0 if and only if the limit of this function jx when x approach x0 equal j at x0. So this was the definition of the continuity of a function in one variable, function j, at a point x0. So the definition of the continuity of the function fxy in two variables at a point x0, y0 in the domain of f will be similar to the definition of the continuity in one variable. So if the limit of the function fxy when xy approaches x0, y0 is equal to f x0, y0, then f is continuous at this point. And if the function f is continuous at each point in the domain, then we will say that f is continuous. So when we say f is continuous, we mean that f is continuous at each point in his domain. Okay, let's take some exercises. Is f continuous? This means is f continuous at each point in his domain? So here the function f is given like this. What is the domain of the function f? So here the domain of this function f is all the points in the plane r squared without the origin 0, 0. Why? Because if we put x power 2 plus y power 2, this part here, we put it equal 0. So we have only one solution, x equals 0 and y equals 0. So this gives me the point xy equal 0, 0. So we must delete this point from the plane r squared. Okay, so the function f is continuous at any point AB different from 0, 0. Yes. Why? Because the limit of fxy when xy approaches AB, if I suppose AB is different from 0, 0, so it will be a times b over a squared plus b squared, and this term down is not 0. So this is fab. So my function f is continuous at the point AB. So now the question, what about the point 0, 0? The point 0, 0 is not in the domain of the function f. Okay, so now any point AB different from 0, 0. So here AB is any point in the domain of the function f. The function f will be continuous at this point. So for this reason, the function f is continuous because it's continuous on his domain at any point in his domain. Okay. Second exercise, the function fxy equals x power 2 y power 2 plus xy power 3 over x power 4 plus y power 4 fxy different from 0, 0. And fxy equals 0, 0, I have 1. Remark that x power 4 plus y power 4, if it's 0, so I will have x equal y equal 0. So this function defined at any point xy different from 0, 0, I can calculate the function f here. Okay. Now remark that the degree of the term x power 2, y power 2 is 4. And your degree of x, y power 3 is also 4 because x power 1 times y power 3, 1 plus 3, it's 4. And down each term of degree 4. So because of this, this part here could be written as a function of y over x because the degree up for each term is 4 and down also for each term. So I will divide here x power 2, y power 2 plus x y power 3 divided by x power 4 plus y power 4. I will divide each term by x power 4. So I will have here y over x power 2 plus y over x power 3 divided by 1 plus y over x power 4. So now this is my function f x y f x y different from 0, 0. Now let's prove that the limit of f x y when x y approaches 0, 0 doesn't exist. We will prove that. How? Let's take at first the line y equal x. Let's suppose that xy moves on this line, y equal x, and approaches 0, 0. So now instead of take xy, I will take xx because y equal x. So let's go back to my function here. So what is f xx? I will put instead of yx, so it will be 1 power 2 plus 1 power 3 over 1 plus 1. So the answer is 2 over 2. So it's 1. So the function fxx approaches 1 when x approaches 0 or xy approaches 0, 0, 0. Okay. Now, the second step, let's take the line y equal 2x. Let's suppose that the point xy, which is equal to x2x now, moves on this line and approaches 0, 0. Moves on the line y equal to x and approaches 0, 0. Then the function f x y will be x2x. So let's write here instead of y to x. So 2x over x, it's 2 power 2 plus 2 power 3 over 1 plus 2 power 4. So it's 4 plus 8, 12 over 16 plus 1, 17. So 12 over 17, it's different from 1. So for this reason, because of this, so now the limit, this limit doesn't exist. And because it doesn't exist, so it's not equal to the number 1, which is here, f of 0, 0. So my function f is not continuous at 0, so f is discontinuous at point 0, 0. The next exercise. The question is f continuous on his domain. If the point xy different from 0, 0, so the function is continuous at this point. So for any point a, b different from 0, 0, then f is continuous at the point a, b. The problem only at 0, 0. So let's take the limit of this term. Now, f the limit of x power 3 over x2 plus y power 2 when xy approaches 0, 0, if this equal to f 0, 0, which is equal to 0, then f is continuous at 0, 0, and so f is continuous on his domain. And the inverse also correct. If the function is continuous at 0, 0, it will be, this limit must be 0. So if this limit is not 0 here on the left, so the function is not continuous at 0, 0, so it's not continuous on his domain. So let's calculate this limit. Let's begin by the idea that x power 2 over x power 2 plus y power 2, this is always greater than 0 or equal 0, and less or equal 1. Why it's less or equal 1? Because you know that if a and b positive numbers, and if I suppose that a greater than 0 and always less than b, then a over b is than 1. Okay? So for this reason, this term is or equal 1. Okay. So now let's product by x. So x times 0, which is 0, less or equal x3 over x2 plus y2 less or equal x. Now, this approaches 0, and this term approaches also 0 when y approaches 0, 0, and also here with when xy approaches 0, 0. So by squeeze theorem, the limit of x power 3 over x power 2 plus y power 2 will be 0 when xy approaches 0, 0. So this proves this limit. So because this is correct now, so my function is continuous at 0, 0, so my function is continuous on his domain. The next exercise. Is the function f continuous? Here we suppose that x is not different from 0, y any number. So here, whatever y and whatever y. So if I put x0 here, so if I put 0 times sine infinity here, sine infinity doesn't exist. It's a number between -1 and 1, but doesn't exist. But we can use also the idea of squeeze theorem. So we can take, if we can prove that, so if the limit of x times sine y over x when xy approaches 0, 0, if this limit equal f 0 and 0, what is f 0, 0? If x equals 0, whatever y, the answer is 0. So this is 0. So if we can prove that this limit will be 0, then f will be continuous at the point 0, 0, continuous at the point 0, 0, then f is continuous on his domain, which is r power 2. So let's calculate this limit now. The question about this limit, how to calculate this limit. Let's take this limit in absolute value. If the answer in absolute value is 0, so without absolute value will be also 0. What is the limit of x absolute value times sine y over x when x, y approaches 0, 0? So it's the limit of x absolute value times absolute value of sine y over x when x, y approaches 0, 0. Now, this term here, sine y over x, in absolute value, it's between -1 and 1. So we have sine y over x, absolute value, between 0 and 1, because I have absolute value. If it's without absolute value, it's between -1 and 1. Between 0 and 1. So let's product by x absolute value. So x absolute value times 0, 0, this or equal x absolute value times absolute value of sine y over x, this or equal 1 times the absolute value of x, it's absolute value of x. Now what is the limit of this term on the right and on the left when x, y approaches 0, 0? And here x, y approaches 0, 0. The answer is 0. So by squeeze theorem, so now the limit, let's write in red, the limit of this absolute value, this term here, let's write it like this, x sine y over x in absolute value equals 0 when x, y approaches 0, 0. But you know that if the answer in absolute value 0, so without absolute value 0, so the limit of x times sine y over x will be 0 when xy approaches 0, 0. So we proved this formula here. So after the answer here equal f0, 0, so my function is continuous at the origin, and so it's continuous on R squared. The next exercise. So here, what is the difference between this exercise and the previous one? The previous one, we have x here times sine y over x when x different from 0. But here, sine without x outside. So now here, if I put x 0 and y, for example, 1, or any number, so the answer will be number over 0. So it's infinity, sine infinity doesn't exist. I forgot something in the previous exercise. So here, someone will ask maybe that why we are studying at 0, 0, because here only x 0, y any number. Okay, let's suppose y equal any number b. So we can study at 0b. Let's write in green. So at 0b. Okay, whatever b. Okay, so f, what is f0b? It's also 0 from here. Okay, so we can write instead of 0, 0, 0b and all of the exercise 0b, 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 etc. So it will not change anything. So for any point 0b on the y-axis, so the function is continuous at this point. And so it's continuous on R squared. Okay, let's continue. Now here, to study this, the continuity of this function, let's prove that the limit, now the idea that if the limit of sine y over x, the answer equal 0 when xy approaches, x must be close to 0, y any number. If this limit is always 0, which is f of 0b, then f is continuous at the point 0b, then f is continuous on his domain r squared. But let's prove that this limit here doesn't exist at the point 0, 0. Let's prove that it doesn't exist at the point 0, 0. So f is not continuous on his domain. To prove this, let's take two lines passing through the point 0, 0. The first line, y equal x. The second line, y equal 3x. So in this, for the first one, the point x, y, when the point x, y moves on this line, so this point will be x, x, and this point approaches 0, 0. So what the limit of fxy will be fxx. So here sine, when x approaches 0, so it's close to 0 but not 0, so I will use the formula here. It's sine x over x, so it's sine 1 radian. On the other line, y equal 3x, and also remember that the point 0, 0 exists on this line. So xy will be x3x, approaches 0, 0. Then the function fx3x will be sine 3x over x. It's sine 3. So they are different because of this. So this limit, the limit of sine y over x when xy approaches 0, 0 doesn't exist. So because it doesn't exist, so it's not equal to f0, 0, which is 0 from here. So f is not continuous. Not continuous at 0, 0, and so it's not continuous on his domain r squared. Next exercise, the function fxy is given by y ln 1 plus x power 2 over x power 2 when x different from 0, and y when x equals 0. So here, let's take any point here, 0. I take any point x, 0, y, any number, b. So f, the limit of fxy when xy approaches 0b, if the answer is equal to f0b, which is b, then f is continuous at the point 0b, then f is continuous on r squared. Okay, so let's calculate the limit of fxy when xy approaches 0b. So I will take this formula here. So remember that when x approaches, what is the limit of this term? Let's write in blue. What is the limit of 1 plus x power 2 over x power 2 limit of ln. What is the limit of when x approaches 0 of ln1 plus x power 2 over x power 2? So if you put x 0, so ln1 over 0, so it's 0 over 0. So you can use Hopital. So this limit for a function in one variable. Okay. So here I will take the limit of the derivative of ln1 plus x power 2. It's 2x over 1 plus x power 2 divided by, this is the derivative of ln1 plus x power 2. Derivative of x power 2 to x when x approaches 0. So I will delete 2x with 2x. So I have the limit of, let's write in blue. So it's 1 over 1 plus x power 2, 1 over 1 plus 0 power 2. So it's 1. So the answer of this limit is 1. So for this reason, the limit of y times ln 1 plus x power 2 over x power 2 when xy approaches 0b equal, I will put instead of yb times the limit of this term when x approaches 0, 1. So the answer is b, which is f0b. So this is, now this formula is correct. So because of this, now the function here f is continuous at the point 0b, so it's continuous on his domain R squared. The last exercise, the function of xy equal ln x plus y minus 1, if x plus y greater or equal to, and here if xy less or equal to. So to understand only that each domain here, if I call this region D1, I call this region D2. So how to sketch D1 and D2? So here in the question, we must change something. There is a small mistake. We must write here. This is less x plus y greater or equal to, and here x plus y less, strictly less than 2. Okay. Now let's sketch the region D1. How to sketch, or let's sketch D2 at first. How to sketch D2? So we have x-axis and y-axis. So this is y-axis, this is x-axis. Let's sketch the line x plus y equal 2. So if I suppose this is 2, and here also 2, let's sketch the line in red, for example. So this is the line x plus y equal 2. Okay, then where is the region D1? The region D1 is here. D2, let's find the region D2 at first. So D2 is here. Okay, all of this part under a line, but because I have strict x plus y smaller than 2 without equal to 2, so it's without this line. So this line is not included. Okay, where is the region? D1. D1 is here. Okay, to verify, let's take any point like 0, 0. Put x0 here and y0 here. So 0 plus 0 is than 2. Take any point here like x0, y3. Put x0 here, y3. The addition greater or equal to. So the region D1 will be with the line. So this line is included in the region D1. Okay? Now let's solve the exercise. So here, let's take any point here on this line. Okay, so the coordinates of this point will be x0, and instead of y0, 2 minus x0. Yes, so let's prove that the limit, let's search the limit of fxy when xy approaches x0 and 2 minus x0, if the answer equal to fx0 2 minus x0, then f is continuous. F is continuous at the points x0, 2 minus x0, and so continuous on R squared, all of his domain. Okay, let's calculate this limit now. Let's calculate, let's verify, is it correct? Yes or not? So let's write the limit. What is fx0 2 minus x0? Because this, if I take x0 plus, this is x and this is y. What is x plus y here? X plus y equal 2. x0 plus 2 minus x0 equal 2. So because I have equal here, so I will use the formula here. So it's the limit of ln x plus y minus 1 when xy approaches x0, 2 minus x0. So it's equal to ln, let's write instead of x, x0, instead of y, so plus, instead of y, 2 minus x0 plus minus 1. Minus 1. So this is x0 plus here it's y minus 1. So this is equal to ln 2 minus 1 is 1, ln 1 is 0. So the answer is the same as f x0 2 minus x0. So the function f is continuous on his domain.